I am Michel Brune from Paris, from Laboratoire Kastler-Brossel. I'll start this and that. And indeed, it is a pleasure for me to be there. And I would like to thank also the organizers of this school. So the topic of my talk, of my lecture, will be twofold. First, in the three first lecture, I will talk about cavity QED and about the kind of experiment we performed in Paris with a very specific system made of high Q cavity made of superconducting mirrors, where photons are stored for a very long time. And when we use Rydberg atoms to investigate the properties of this field, and we use this system to illustrate some very important properties of quantum theory of measurement, especially. So I will focus on aspects related to the investigation of quantum theory of measurement using the tools of cavity QED. And the second part of my talk, I will talk about quantum simulation. So now Rydberg atoms became a very popular way for building quantum simulator with trap single atoms in optical tweezer. And so the second part of the lecture will be devoted to this system. So now let us introduce the cavity QED topic from the point of view of realizing with a real experiment some of the Gedanken experiments introduced by the founding fathers of quantum mechanics. And indeed, I would like to start just with this citation of Schrödinger. Probably most of you already read that. One never experiments with just one electron, one atom, or one molecule. In thought experiment, we sometimes assume that we do. This invariably entails ridiculous consequences. And indeed, it shows this sentence contains two very important messages. First, the founding fathers of quantum mechanics were very aware of the complexity and the difficulty of quantum theory, especially when applied to single quantum system. And the ideas around that, which was considered as strange phenomena predicted by quantum theory, was, for example, the existence of quantum jump or the possibility to have a so-called Schrödinger cat state, a cat in a superposition state of dead and alive state. So Schrödinger was aware that in the quantum theoretical framework, these objects exist, but he considered them as unphysical, so as ridiculous. And the way to eliminate this kind of ridiculous thing was very empirical. He said, okay, theory contains that, but experiment will never be able to access this regime. And indeed, what I'll try to show you in the first lecture is that indeed it's possible to manipulate single system and to explore the ridiculous aspect of quantum theory, which are not so ridiculous, they are counterintuitive, but they exist, and they were demonstrated not only in the cavity QED setup, but in many other setups. So before starting, I would like also to say that this is a lecture, so you should interrupt me at any point where things are unclear, instead of waiting for the end of the lecture for asking questions. So please interrupt me. I would be happy to answer questions directly. So among the systems we can have in mind, realizing the manipulation of single isolated quantum system. Indeed, there are many different systems which are listed here. This list is probably not exhaustive. So I mentioned here the photons, which can be produced very efficiently in pairs of photons with polarization entanglement. Cold atoms, now you have all seen this picture where in the atomic microscope experiment you see cold atom in optical lattices which are resolved one by one. photons or single photon emitters like quantum dots can emit a very well-controlled way single photons. Mesoscopic circuits made of superconducting material and Josephson junction, the so-called artificial atoms, are very beautiful system for investigating the properties of single quantum system, and indeed are very closely related to the cavity QED system I will discuss in my lecture. And of course, the ion trap system is already very famous for the manipulation of single particles, single ion, as shown by the work which was performed by David Wineland in Boulder, and which together with Serge Haroche got the Nobel Prize in 2012 for very similar work performed either with single ions or with single or a few photons stored in a high Q cavity. So here I will focus on the cavity QED part, but you have to keep in mind that all the concepts which are investigated there were more or less in parallel also investigated with the single ion or a few ion system, where the field mode plays the role of the motion of the ion, which is harmonic oscillator, and the two-level system, instead of being Rydberg atom, it's single ion trapped in some electrostatic electrodynamic trap, like a pole trap used by David Wineland. So that's the general context, and now I'll focus on the cavity QED system. And as I told you, the first lecture will be devoted to this system, whereas the two last ones I will deal with a single atom trapped in optical tweezers and the quantum simulations which can be performed using interaction between these atoms mediated by excitation to Rydberg levels. So before starting the formal description of the system, I would like to start with some historical introduction of the topic, because I think it's always good to have in mind that everything was not invented yesterday, and there was a long way to where we were. So this long way can be tracked back for cavity QED. The oldest reference I found related to that is between the story started in 1870, and this period lasts up to 1920, up to more or less the starting of quantum theory. And at that time, people were dealing with classical electrodynamics, so they knew a lot about that. And they were aware that dipole radiation, and here, when we are talking about dipole radiation, we have in mind a macroscopic antenna radiating a field. This radiation diagram is affected by the presence of conducting surface. So people were aware of that because it's in the Maxwell equations. And basically, they studied this, especially in the context of the radiation of an antenna in the presence of the Earth, which can be considered as a conducting media for radio frequency waves. So this was all classical thing. And then the thing becomes quantum, and quantum investigation about interaction between atom and metal was investigated in 1930, so about 10 years after the start of quantum things, with London and Lennard Jones. And then a very famous step is 1946, where a Purcell realized that when spin are coupled with a tuned resonator, the spontaneous emission rate can be very significantly affected. And I like very much to show the paper where he predicted this effect. It's a very short paper published in Physical Review in 1946. So that's the full length of the paper. It looks like an abstract, and it's very dense and compact. And this was enough to explain that also the lifetime of a spin, of a nuclear spin by spontaneous emission is like this huge number if you have it in free space. So this number, 5 × 10⁻21, is like 3 orders of magnitude longer than the age of the universe, which is only 10⁻18 seconds. So this is a really huge number. And indeed, you can make it of the order of 1 minute or a few minutes if the spin is coupled to an electromagnetic environment which is changed by the presence of a cavity. And introduced in this paper the very famous formula where he explains that the spontaneous emission rate is enhanced what's the so-called Purcell factor, which is written here, which is a product of the quality factor of a resonance mode multiplied by the square of the wavelengths divided by the volume of the mode. And the idea is that this number can be huge and it will affect spontaneous emission because this number corresponds to a variation of the density of mode, which is coupled to the atoms and which is present in the Fermi-Golden rule. And basically, he had a very simple argument to estimate this density of mode. He says that when you have one resonance, it's one mode within the width, the frequency width of the resonance. If the width is very narrow, the density of mode is very high, even if there is a single mode. And the second ingredient is that the coupling strength with this mode is proportional either to the amplitude of electric field or magnetic field in the mode, which is stronger if you confine the single mode fluctuation in a very small volume. So there are two effects, quality factor effect and mode volume effect. So this is amazing that such a short paper give rise to so many different applications. And indeed, it took time to observe this. I will come back to that in a few minutes. So after this prediction by Purcell, the next important step is Casimir effect, which was introduced by Casimir, and which deals with the force between two conducting plates related to the energy of vacuum fluctuation between the plates. And when you change the plates, you change the structure of the mode between the plates, and then vacuum fluctuation have to follow the boundary condition imposed by the plates, and it reduces some attractive force between the two plates, the so-called Casimir force. Then Schwinger studied the boundary effect on synchrotron radiation, so it was the beginning of the physics of accelerator. People realized that accelerated particle radiates, and this radiation is interesting, and the way they radiate depends on the boundary condition around the charge which are accelerated. Then in 1954 and then 60 comes the times of laser and maser, where the emission process responsible of the radiation is stimulated emission of a photon by in a mode which is stimulated by the presence of a cavity, as all of you know for lasers and masers. And then we go closer to single particle effect with a work by Rydberg in 1974, when he first observed a modification of molecular fluorescence near surfaces. So it's already it can be traced as the first manifestation of the Purcell effect. And then in the 80s, modification of spontaneous emission was observed for single atoms in various experimental setups. So at the ENS in the group of Serge Haroche, I will tell you a bit about that, but also in MIT in the group of Dan Kneppner and at many other places in the world. And so here I would like to mention indeed the first experiment performed at École Normale, which was the first demonstration of the Purcell effect with single atoms. So this was realized with Rydberg atoms of sodium, I think. And indeed, the enhancement of spontaneous emission was observed on a transition between the two Rydberg level 23S and 22P. And here what you see, it was we call the ionization signal. So once we prepare a Rydberg atom, we can ionize them by applying an electric field. And when we increase the amplitude of the electric field, the more bounded the levels, so which have lower energy, ionize in a higher field. So here you can identify two peaks corresponding to ionization of Rydberg levels, either in 23S level, that's the level in which they are prepared, or for a bit higher field, the 22P level. So atoms are prepared in 23S levels. They are placed in a high Q cavity with a quality factor of 10 to the 6. So it's not the highest possible quality factor, but it's already quite significant. This was a superconducting cavity. And one observes that when the cavity is tuned, you go from the blue line to the black one, where the population of 22P level becomes very important as a result of acceleration of spontaneous emission. So I like this figure very much. It's from a work from Serge Haroche, Jean-Michel Raymond, and Michel Gross and Philippe Bois. This work was performed before I started my work in the team. And indeed, you can see the handwriting of Jean-Michel Raymond commenting these signals on a very old slide. So it was the demonstration that spontaneous emission can be altered by orders of magnitude. Here the acceleration factor was 500, which is very significant, just by dealing with cavity mode and controlling the boundary conditions of the field around the atoms. So that's the historical part. And indeed, all these experiments up to that point were performed in the so-called perturbative regime. The perturbative regime means that you can still describe the interaction with light using perturbation theory and Fermi golden rule, and that basically evolution is irreversible evolution, even if faster as compared to free space. Indeed, the very next step is to go in the so-called strong coupling regime, where the spontaneous decay is, disappears and is replaced by coherent evolution, the so-called Rabi oscillation, where the atom and the field exchange coherently this energy. So we'll describe this formally a bit later in the lecture, but I would like here also to discuss the first experiment demonstrating this effect, which is the so-called micro-maser experiment, which was performed more or less in parallel at École Normale and in Munich in the group of Herbert Walter. And here is depicted the experiment performed in Munich, where the Rydberg atoms were prepared in an atomic beam. They were crossing a high Q superconducting cavity, which was a closed box, so a cylinder closed at both ends, and with small holes on the axis, which were small enough so that the microwave, the hole diameter was small enough so that we were below cutoff for the microwave transmission, which means that a microwave photon emitted inside the cavity cannot leak out, and as the mirror were superconductor, the quality factor was very, very high. And after interaction with the field in this cavity, the atoms were detected one by ionization, so the process I already introduced. We apply electric field, get some charge, which are easily counted using a channeltron. And here is the number of atoms detected as a function of cavity detuning, so that the population of the initial state, which is the 53P level, which drops when we get across resonance on this transition. So in this experiment, the atomic flux was so low that atoms were interacting one by one with the field. And basically, interaction time was close to a pi pulse, so that one excited atom performs Rabi oscillations, emits the photons, leaves the cavity, is detected, and this atom sees this photon and have even accelerated Rabi oscillation by stimulated emission, and this produced the so-called micromaser with an emitting active maser made of a single atom at a time, and most of the time the cavity was empty, but it was sustaining the cavity, the microwave photon for long enough time so that the field does not disappear between two atoms. So that's a very famous experiment, this micromaser experiment, and I think it's important to have it in mind. So then, in the historical overview, I already pointed out the two very important regime of cavity QED, the so-called weak coupling regime, in which basically, qualitatively, the behavior of the atom due to interaction with radiation is exponential decay, and just the decay rate is affected by the presence of the cavity. And the strong coupling regime, where the coherent interaction between two-level systems overwhelms dissipative processes which can be neglected in first approximation, and then you are dealing physically with coherent energy exchange between the atom and the cavity field. And indeed, this coherent exchange corresponds to the Rabi oscillation of a two-level system. So that's the two regime, and of course the second one is very interesting for probing the fundamental aspects of quantum theory, because it's a way to control a variety of atom field and tangle state, to prepare a pure state of the field, and really to probe the properties of quantum theory in this very idealized situation. So now I go progressively into the more technical part by listing here the various time scales which are relevant in this cavity QED context, and which have to be compared in order to have a clear view of the physics of the system. So the first two time scales are the dissipative time scale that you have to overcome in order to go in the regime of coherent evolution of the system. So the atomic level lifetime is nothing else than the lifetime of the upper state of the system. The cavity photon lifetime, which is the storage time of photon in the cavity. So if you put some field, a classical field in the cavity, it decays exponentially with some time constant, which is Tc, and with a rate that I name kappa. And indeed, if the field is not classical but a quantum field, the average field decays with the same rate. So this is not a property of a quantum field; it's a general property of energy decay in a cavity. Then, a very important parameter: the coupling strength between a single atom and a single photon in the cavity. So here it will be depicted by omega naught. And in literature, another notation is very common, is 2G for omega naught. And indeed, it's proportional to the inverse of the period of the vacuum Rabi oscillation. And this can be also named the vacuum Rabi frequency. And then the atom cavity interaction time, because it's not enough that the coupling is strong, that omega is larger than damping rate, but you need also that you have the long enough time to observe coherent evolution. So that's described by the interaction time. And the strong coupling regime is characterized by the product of interaction time times vacuum Rabi frequency larger than 1, much larger than 1, and negligible dissipation as compared to coherent evolution. So the time scale related to damping should be much longer than the time scale related to coherent evolution. And then with these tools, when you have in a strong coupling regime, many different systems can be investigated demonstrating the strong coupling regime of cavity QED. So I will not cover all the systems in my lecture, but I would like to mention them with the characteristic order of magnitude of the parameters for the system. So I will not tell all the numbers, but it's very important to mention optical cavity QED, where instead of Rydberg atom in superconducting cavity, which have transition in the microwave regime. You can have typically alkali atom trapped one by one in some resonance mode of an optical cavity, and where basically the resonance transition of alkali atom, when resonant with the cavity, leads to strong coupling regime, provided that you have very high quality mirrors. There are optical mirrors reaching quality factor of up to 1 million. And then you put the mirror very close together so that the mode volume is small enough to get these numbers characteristic of the strong coupling in optical cavity QED. And then you have a very nice tool to manipulate not only the atom, but the field. And the field which goes out of the cavity is a very important aspect of this optical cavity QED experiment. Indeed, I will ignore this because in the case of microwave QED, we don't want that the photons leaks out of the cavity, because microwave photons are diffracted in all space. They do not propagate like nice Gaussian beam, and so we are not interested in the field radiated to the cavity. On the contrary, in optical cavity QED, the interesting field is a field going out of the cavity, and I think that the next lecture will deal with this kind of concept. Then solid state cavity QED, where you can have a single solid state emitter, like a quantum dot, embedded in the Bragg mirror structure, where the strong coupling regime is reached with timescales much faster than in the optical system with single atoms. Circuit QED, where the solid state qubits are made of Josephson-Johnson and superconducting circuits, where also the coupling is very fast, and the factor of merit is as good as the microwave Rydberg atom cavity QED experiment. And so the microwave cavity QED, on which I will focus, and in which the coupling strength, the vacuum Rabi frequency in the range of tenths of kilohertz, the cavity, the damping rate of the cavity is like 1 hertz. So it means that the decay time of the field is the range of a fraction of a second. The lifetime of the atom corresponds to a line width of atomic transition of 30 hertz, and the interaction time can be as long as 400 microseconds, limited by the velocity of the atoms when crossing the cavity. Indeed, we are here considering experiments with atomic beam, most of the time without using cooling technique for slowing down the atoms. So again, the fine structure of the talk. So today I will focus mainly on the strong coupling regime and develop the formalism used to describe it, and describe the first experiment demonstrating this strong coupling regime. Then in second lecture, I will show you how you can use the strong coupling regime in order to perform a very quantum measurement of the field photon number in the cavity by performing a quantum non-demolition photon counting experiment, demonstrating one of the ridiculous things considered by Schrödinger, which is the quantum jump. So there is a very famous paper by Schrödinger when he asked the question, does quantum jump exist? And the conclusion is that it will never exist, and indeed it does. And then the third lecture will be also related to quantum measurement, but going a bit more in the macroscopic direction and looking at what happened between some information stored in a microscopic quantum system is transposed into our classical world in the form of a measurement result. And so it will deal with the physics of the transition between quantum behavior and classical behavior, illustrated by the Schrödinger cat problem, and that we will investigate also from the point of view of a real experiment. So this course today, I will first introduce the formalism, the so-called James Cummings model for describing one atom coupled to one mode. And then I will present you the experimental setup that we used to investigate that, and describe first experiment demonstrating Rabi oscillation in a small field stored in the cavity. So one atom, one mode, the James-Cummings model. And indeed, the James-Cummings model is the generic Hamiltonian for describing a very a very simple quantum system made of, I would say, one spin and one spring, because it applies to any kind of oscillator, even a mechanical one. So the spin will be a two-level atom with upper level that I will name E and lower level G. In case of Rydberg atom, G is not the ground state of the atom, it's another Rydberg level, and both levels have a finite lifetime. But lifetime is so long that we can neglect it as a first approximation. Then the spring is any harmonic oscillator, so it will be a cavity mode in our case, described by in the number state basis, or the Fock state basis, by energy levels, which given number of photons. And then the interaction will be characterized by the so-called vacuum Rabi frequency I already introduced, which is here the parameter omega naught. And so now let us introduce the first partner in the formalism, which is the quantum description of the field. So I assume that you already heard about field quantization in free space, and I will not, of course, do a lecture about that, but I want to point out what is different and what is similar when we quantize the field in a cavity. Because a priori, quantizing the field in a cavity is a very complex problem, where you have not only the electromagnetic field, but all the charge in the mirrors which are involved, and that's a huge number of degree of freedom of system. And indeed, the miracle is that this huge number of particles, all the atoms and all the charges in the mirror are coupled to the electromagnetic field, but you can describe the field without taking care of detailed microscopic description of all these particles by applying this standard quantization procedure, which basically consists in first ignoring quantum theory and finding, with just the tools of classical electrodynamics, finding the so-called eigenmodes of the cavity, so the resonance frequency of the cavity, which means that using Maxwell equation, you solve this Maxwell equation, including boundary conditions imposed by the mirror. And here, the presence of atoms and electrons in the mirror is just appear as a condition at the limit of the electric field. So you solve the Maxwell equation in presence of boundary condition, and you find a general form of the electric field for a mode. So it's not very original formula, which is here the electric field amplitude as a function of position of time. So there is some normalization factor, which is common to introduce here. There is then this function of position, which is in general complex and which describes the shape of the mode of electric field. So if your cavity is made of two planar mirrors, this is just the plane wave structure with exponential IKR that you know. If cavity is more complicated, it's some function, and if your cavity have a proper shape, this will be, for example, the shape of the Gaussian mode, which is sustained by our cavity made out of spherical mirrors. Then there is a time dependence and complex conjugate to make the thing real. So when you go to the quantized field, and I'm sorry, there is a screwy here in this formula, but I will remove it later. So here, when you quantize, the trick is very simple. It's interesting to introduce in the classical formalism the complex dimensionless amplitude of the electric field, a parameter alpha, which is a dimensional sim number, and all the dimension factor of the electric field in this factor E. And then when you quantize, you replace the dimensionless complex amplitude by quantum operators, the A and A dagger operator of creation and annihilation of the electromagnetic field. And indeed, this formalism holds for any harmonic oscillator. You write the amplitude of the field using a dimensionless dimensionless complex amplitude, and when quantizing, this dimensionless amplitude becomes an operator. And the miracle, which is maybe not a miracle, is that then the Hamiltonian is just the sum of the Hamiltonian of individual harmonic oscillator if you consider many modes of the cavity, which means that all these modes behave independently without being coupled to each other. So this is the fundamental formula for the expression of the quantum field operator. And here is, of course, the fundamental commutation relation of the two operators A and A dagger. So now this parameter, what does it mean? The E omega, the amplitude of electric field. Indeed, for classical field, there is no scale, no physical scale setting the magnitude of the electric field. And what I put here, a dimensionless number, there is a degree of freedom in choosing the magnitude of this normalization factor. But if I go to the quantum, the physics goes in, and this amplitude is related to the amplitude of vacuum fluctuations. And then you can recognize in this formula h bar omega over 2, which is the zero-point energy of harmonic oscillator, distributed over a volume, which is a cavity volume, and epsilon 0 is there, so that when you take the square root of this, you get the dimension of some electric field. And so this parameter in the quantum formalism is not an arbitrary number. It's really related to the strength of vacuum fluctuation in the cavity. And when you add one photon in the cavity, the field, the change of the field is related to the matrix element of A and A dagger when acting on one photon field instead of vacuum, and the field becomes larger proportionally to the square root of the photon number in the cavity. So that's a very important parameter, and it's related to a geometric parameter, the volume of the mode of the cavity, which is formally defined once you know the distribution, the spatial distribution of the field, properly normalized. Then this integral defines the cavity volume. Of course, if you have a Gaussian mode, transversally the Gaussian goes to infinity, but this integral is finite, and the volume is basically the square of the waist of the mode multiplied by the distance between the two mirrors. So that's the ingredients. That's enough for describing the field. Single harmonic oscillator and an amplitude characterized by this number, which corresponds to vacuum fluctuation amplitude. And here, I would like to emphasize again that it's a very simple answer to a priori very complex problem, which is the coupling between all the charge in the mirrors and the mode of the cavity. Indeed, this problem is solved by using the notion of mode. And every time in physics, with any very complex quantum system, is you can define a classically harmonic modes, then the quantization of these harmonic modes is straightforward, independently of the complexity of what is behind. So that's a very important message. So now we consider a single mode, and we'll do not use index for representing the different modes. So for this mode, I write in here the James Cummings Hamiltonian, which basically is the coupling between two atomic levels with a transition frequency omega hat, and here I depict the cavity frequency by omega c. And then the atom field Hamiltonian is the sum of three terms. The first term is the purely atomic Hamiltonian, and I write it h bar omega hat over 2 times this difference of two projectors. Here I choose the energy origin for the atomic system just halfway between the two levels E and G. Then the cavity Hamiltonian is that of a single mode harmonic oscillator with again the operators A and A dagger. And then the coupling in the case of Rydberg atom is dominated by electric dipole coupling, which is the product of the dipole operator times the electric field operator in the cavity. And the dipole operator is a product of a number, which is a vector because it has 3 components, depending on the choice of S, P, D levels and polarization of the mode. And this is not a projector, but it's a common way to write the off-diagonal elements, matrix elements of dipole in the atomic basis E and G. So that's a very usual way. Usually, this can be also be written in terms of effective spin by replacing the notation EG by spin up and spin down, and then you can use poly matrices. So the Hamiltonian of the atom is proportional to sigma z, and the interaction Hamiltonian here is a combination of sigma plus and sigma minus for the dipole matrix element. Then it's important to keep in mind the condition of validity of this Hamiltonian, which makes first, on the atomic point of view, two-level system approximation. So if you are dealing with a spin 1/2, it's a real physical two-level system. When you are dealing with Rydberg levels, you are dealing with infinite number of levels. And indeed, the fact that you choose to privilege a pair of levels corresponds physically to the fact that the cavity frequency is supposed to be close to an atomic transition, so that the resonance condition enhances the interaction between a given pair of levels and the mode of the cavity, and all the other atomic pairs of levels are completely non-resonant with the cavity field and will not be significantly coupled due to interaction. This approximation eventually breaks down if you make the intensity of the field in the cavity go to infinity, so that the Rydberg frequency becomes of the order of spacing between energy levels, but that's not a regime that I will consider here. So the other important parameter is that you have a small cavity for this two-level approximation, and to have this Hamiltonian valid, where here I neglect dissipation. And small cavity means that you have only one mode which is close to resonance, because the distance between the different modes in the cavity for a small cavity becomes large enough so that if one mode is resonant on one atomic transition, there is a very little probability that the second mode becomes resonant with another transition. So it's important that the cavity is small, not only so that the cavity volume is small, but also that the free spectral range of the cavity is large and the single mode is at resonance with the atom. So that's the basic fundamental step for describing this system, and that is the James-Cummings Hamiltonian. So let us solve this Hamiltonian, which is very simple because it boils out that it results only in coupling between pairs of levels. So how does it work? Here I developed the product of the dipole operator times the electric field operator. And so there are 4 terms when you develop the sum of A plus A dagger together with the sum of the operator EG and GE. And then we make an approximation which is basically consists in discarding these 2 terms in red, which correspond to couplings with states which are completely off in terms of energy. So this term will couple an initial state where the atom is in G and the field contains 1 photon to the field with less energy. So this term, when you apply it to an atom to G, will excite the atom, and okay, it's the opposite color. Okay, so I'm sorry, I should have discarded the green terms and not the red one. So here, if you apply this operator to G, you excite the atom, and Heidegger creates a photon in the cavity, which the energy of this level is the double of the initial energy, and so this is a non-resonance term. On the other hand, the red terms here, if you apply it to E, it couples E to G, and then it emits a photon which is created by the Heidegger operator, and the final state has the same energy, or nearly the same energy, as the initial term. I add the bar too fast. So then, if you neglect this term, you deal with this Hamiltonian, which have only two terms left. And here again, I write the expression of the vacuum Rabi frequency, where one player is the vacuum, the amplitude of the electric field in the cavity, and here the magnitude of the dipole matrix element between the two Rydberg levels that you can compute. And then here is the expression of the Rabi frequency, and the rotative wave approximation, which consists in neglecting the two green terms, is valid provided the vacuum Rabi frequency, eventually vacuum Rabi frequency times the square root of the number of photons, remains much smaller than the atomic frequency. Okay. And then we can solve this Hamiltonian, which basically couples the levels only by pairs. So here on the left, you have the bare state of the system without coupling, with the absolute ground state, which is the atom in level G and the vacuum field. And then if you consider the first excited state, if the cavity and the atoms are at resonance, you have degeneracy between excited atom with 0 photon and atom in the lower state with 1 photon. And as a result of this Hamiltonian operator, you get off-diagonal coupling between these two states, and you can diagonalize very easily the 2 by 2 corresponding matrix, and you find this value for the eigenenergy of the levels, which is written here not just for one excitation in the system, but in the general situation where the field contains n excitations, and when you have degeneracy between these two levels. And so you introduce two coupled eigenvectors, which are positive and negative superposition of the two bare states with eigenenergy here, which is the energy of the free atom and free field, plus the coupling energy, which is nothing else than the splitting between these pairs of levels. And that's it. So very simple formalism. I will not need more complicated theoretical framework than that to describe the strong coupling regime of cavity QED. And then the interesting thing to consider is the time evolution counterpart of the structure of the spectrum of energy level. As you know, when you have pairs of level, and if the initial state is not an eigenvector of the level, you can compute easily the evolution by decomposing the initial state over the eigenvector of the system. And the result of the calculation is a so-called Rabi oscillation, which in case of vacuum in the cavity takes this form. It's a coherent oscillation of the system between the initial state excited atom in the vacuum and the other state which is coupled to it, which is the atom in the ground state with 1 photon in the cavity. And this occurs at the vacuum Rabi frequency omega naught, which in the experiment is typically 50 kilohertz. So that's the heart of the first experiment I will describe today in the next part of the lecture. And then I will talk about the experimental tools which we realize to achieve this strong coupling regime with the Rydberg atom in a superconducting cavity. So let's start with the so-called photon box. And indeed, what is the shape of this photon box, which is used to trap the photon for long enough time so that coherent evolution occurs before the photon disappears out of the cavity due to imperfection. So this is a superconducting cavity, and indeed that's really the heart of the experiment, the realization of very high Q superconducting cavity. The shape of the cavity is, it looks like spherical mirror. Indeed, it's not spherical, it's toroidal to remove the degeneracy between the two polarization modes. So only one polarization mode of the cavity is made resonant with the atoms. And then the metal we use is niobium, which is a good superconductor for microwave, provided it is put at low enough temperature. Indeed, all the evolution of the experiment I will discuss today, but also in the other lecture, is related to what we call our version of the Moore law, which is the progress we made in the fabrication of the cavities, with the first cavity realized in 1994, which had a lifetime of only 2 microseconds, which was not yet in the strong coupling regime. And indeed, at that time, we did an interesting experiment with Paolo Nussensweg, that you eventually know. We performed a PhD in our experiment. And this was not good enough to be in a strong coupling regime with a single photon in cavity, but it was good enough to observe the effect of vacuum fluctuation on the atom and to observe a modification of the lamp shift experienced by the atom and related to the coupling with the single cavity mode. But I will directly jump to the cavity we realized in 1996, where the quality factor was 2^10⁸, corresponding to lifetime of photons in the cavity in the range of 50-100 microseconds, so a longer time scale as compared to the vacuum Rabi frequency. And in the last lecture, in the second lecture and the last one, I will go to that point that we achieved in 2006. So you can see that over time there was a 10⁵ variation and improvement of the quality factor of the cavity, and it was really a fight to get this factor. And indeed, the nice experiment I will present tomorrow and the day after tomorrow would not have been possible without this. So it was really, in terms of time spent in the lab, a very long work to get this improved cavity. So in the experiment, the second ingredient is the Rydberg atoms I already introduced, but it's very special Rydberg levels that we use in this experiment, which are so-called circular Rydberg atoms. So Rydberg atoms are defined by the fact that the principal quantum number is large. I already showed you a first experiment dealing with a principal quantum number 22, 23. Then, if you deal with low angular momentum Rydberg levels, the lifetime is limited by spontaneous emission to very deep level with optical resonances. If we instead use circular atoms, then lifetime is much longer, in the range of tenths of milliseconds instead of hundreds of microseconds. And that's the reason for which we use the circular atoms in this experiment, which are defined by the orbital and magnetic quantum number having the maximum possible value for Rydberg level, which is n-1. And then the cavity is close to resonance with this transition between the circular level with principal quantum number 50 and 51 in this experiment. The transition frequency 51 gigahertz, corresponding to a wavelength of 6 millimeter. And just a kind of word about the phenomenology of the Rydberg levels in order to understand how we isolate the circular one. Indeed, it's not so easy because the degeneracy of Rydberg multiplicity is very high. For a given principal quantum number, n square levels are degenerate. So for n equal 50, for each multiplicity, you have like 2,500 levels which are degenerate. Of course, you cannot consider this as a two-level system. And the trick to make a two-level system out of that is to apply some static electric field, which removes the degeneracy between most of the level through a so-called linear Stark effect. So the level split linearly with the amplitude of electric field. And then if the cavity is close to resonance with this transition, it is not resonant with the other ones, except maybe that one, but with a very weak coupling that we can neglect. And the circular level in the presence of electric field in the cavity are behaving as nice two-level atoms coupled to a single cavity mode. Of course, there is a price to pay. They are not easily excited just by lasers, these circular levels. So here I give you an idea of what we do in order to prepare the circular levels. So we are dealing with rubidium. We start with the upper hyperfine level of rubidium 85 in this experiment. And we first resonantly excite the atom from this level to the 5s level with a laser at 790 nanometers. Then a second step to go to 5D level. Then a third step to go in the 52F level with selecting a specific magnetic quantum number m equal 2. And once you are there, lifetime of this level is in the range of 100 microseconds. So it's long enough so that in the few 10 microseconds you need to circularize the atom. It does not decay. And in order to circularize that, you switch on some electric field. Then the atom follows adiabatically a level with m equal 2 magnetic quantum number. And in some electric field, you have exact resonance between all these transitions, between this m equal 2 level with low orbital angular momentum to the circular levels. And all these transitions are radio frequency transitions with a frequency of typically 200 megahertz. And we perform some adiabatic passage from here to here by having a ramp on the amplitude of the electric field. So you will not need to know all the details about it, but basically you put in a small box all kind of fields you can have to manipulate the atom: laser fields, radio frequency field, microwave fields, static magnetic field, and you get the circular atom with a very high purity, larger than 99%. So it means that the population left in all the other levels of the multiplicity can be neglected, and we'll ignore it in the continuation of the lecture. Then one word about the detection of circular level. I already showed you in the first slide some ionization signals. So once the atom has crossed the cavity, the atomic beam crosses the detector where there is a gradient of electric field, and when we reach the field, the atom reaches the position where they ionize. Some electrons are accelerated to an electron multiplier. And if you vary the ionization field, you see different peaks characteristic of different circular levels. Here, the 52 circular level, 51 circular level, and 50 circular level. And you see that these two peaks are very well separated, so that if you set the field either here or here, you count with very good fidelity either the 50 circular level or the 51 circular level. So then the experimental setup, the scheme looks like this: an atomic beam experiment. So it's no slow atom in this experiment. A box here, which looks like a box because in reality it's really a box. It's a superconducting box where the magnetic field used to prepare the circular atoms is confined so that it does not perturb the atoms when they cross the cavity, and so that it does not perturb the superconductivity of the mirror here. It's not good to have some magnetic field on the very good mirrors because niobium is a type 2 superconductor, and in the presence of magnetic fields, there are magnetic floods which can be trapped and generate dissipation in the mirror. So this is circularization box. We have all the circularization fields there. And in the end, we can prepare in a pulse way. So we pulse the laser excitation, and then we excite on average between 0.1 and 10 atoms per laser pulse. In experiments where we really want to be in single atom regime, we make the excitation strength small enough so that we can neglect the probability to excite a pair of atoms, and the atoms really interact one by one with the cavity. So all this in a cryogenic environment, not only to have good superconducting mirror, so here the temperature was 1.3 Kelvin, but also to avoid blackbody radiation. Because blackbody radiation is the enemy of Rydberg atoms due to their strong coupling to microwave. And at room temperature, you have hundreds of microwave photons which stimulate emission of the atom and reduces the lifetime of the Rydberg atom. Blackbody radiation would also fill the cavity with hundreds of blackbody photons. And we want a cavity in the vacuum. So we really need a low temperature to get rid of the blackbody radiation, and that's done by operating the experiment in 1.3 Kelvin in this first experiment. And then the atom reached the state selective detector where they are ionized. So in reality, it looks like this. So very often experiment looks like a mess because it's done as it is. And here, the green line corresponds to the trajectory of the atom across the cavity. So the gray box here that you barely see is a superconducting block, including the circularization zone for the atoms. And then we have two detectors to count first the 51 circular level and then the 50 circular level afterwards. There are a lot of connections to control the electric field everywhere in the setup along the trajectory of the atoms, where there are many different elements. But today we'll just comment the central element, which is the superconducting cavity. You see one mirror here. Of course, the second one was removed so that you can see something. But here there is a cover of the box holding the second superconducting mirror. And then we did the experiment. We prepared a single atom in the upper state, the 51 circular level, in the presence of vacuum cavity. And here we monitor the population, the atomic population, as a function of interaction time, which scales here is expressed in the microseconds. And you see that the expected vacuum Rabi oscillation is observed clearly. In this experiment, you see oscillations. There are imperfections, which leads to damping. But in this first experiment, we observe a vacuum Rabi frequency of 47 kilohertz, very good agreement with the calculated value from the dipole matrix element and from the geometry of the cavity, with a period of vacuum Rabi oscillation of 20 microseconds. And you see that here, that's a strong coupling regime, where instead of observing exponential decay of the atom emitting a photon in the cavity, you observe the coherent exchange of energy between the atom and the cavity, characteristic indeed of a two-level interaction in a two-level system made of these two states. So there are interesting feature of this Rabi oscillation, especially in the context of quantum information technology and the context of performing quantum gates. So you can look at different specific interaction time of the atom cavity system corresponding to interesting kind of quantum gates coupling the Rydberg atoms and the cavity field containing either 0 or 1 photon, which can also be considered as a qubit. For example, the pi/2 interaction pulse produces a coherent superposition of E0 and G1, and if you put effective spin instead of atomic and cavity system, this is an entangled EPR pair, where if one spin is up, the other is down, and reversely for the second part of the wave function. So this produces entanglement, very interesting for quantum information manipulation. If you make a pi pulse, indeed, you exchange the excitation of the atom into an excitation of the field. So here, the atom is in E state initially, and it writes a field with 1 photon in the cavity. If the atom is initially in the superposition state of G and E, this superposition state will be transferred into a superposition of 0 and 1 photon in the cavity. So you can use the cavity as a quantum memory for the states of the atom that you can recover later with another pi pulse of Rabi oscillation. And another very interesting interaction is the 2 pi pulse. So here it seems that nothing happens because you come back to the initial state. But indeed, a very interesting thing happened for quantum information. Indeed, if you consider these two levels have two states of an effective spin 1/2, if you rotate a spin 1/2 by 2 pi, you come back to the initial state with a phase shift of pi. You have a minus sign which appears there. And that's the core ingredient for performing a quantum phase gate between the two qubits. So I will not focus on that in this talk, but here you have an interesting ingredient for performing quantum gates in the context of quantum information manipulation. So then I jump in the future of this graph to 2019 to show you another experiment where we demonstrate the strong coupling and the Rabi oscillation, but over a much longer time scale. So what did we for that? Indeed, the quality factor of the cavity was much better. But the second thing we did is that we used much slower atom to increase the interaction time. So we built a kind of atomic fountain experiment with here a 2D mode cold atom source, sending a slow beam of ground state atom of rubidium with typical velocity of a few 10 meters per second. And then interaction time can be as large as 400 microseconds instead of the 80 microseconds achieved in the previous experiment. Then we made progress about the cavity technology. I will come back in the second lecture about this progress, but we reached the cavity storage time of 8 milliseconds instead of hundreds of microseconds. So then we perform again the Rabi oscillation experiment with this cavity. And indeed, we observe these very nice new Rabi oscillations with a negligible damping if you compare to the previous version of the experiment. So this was limited partially to the finite cavity damping time, but also by crosstalk between different detection channels, which can be eliminated. And so we reach this regime where basically over a time scale of 400 microseconds, when you fit a damp sign function of the signal, you find practically no damping over this time scale. And so you are dealing with a very pure, coherent evolution of the system as compared to the initial experiment. So then we'll deal with what happened when instead of making the atom interact with a vacuum, it interacts with a small coherent field stored in the cavity. And it will give me the opportunity to introduce formally a very important ingredient for the experiment and for the next lecture, which is what we call coherent field states or Glauber states of the electromagnetic field, because these states were first introduced by Roy Glauber in order to describe quantum electrodynamics effects. So what is the coherent state? Indeed, we already introduced the very simple states with a well-defined photon number in the cavity, the so-called number states, depicted here by this N. And indeed, the quasi-classical states are very different from the number states. For example, a number state have a perfectly well-defined energy, but a completely undefined phase. If you calculate the average amplitude of an electric field, it's 0. So it's purely a fluctuating field, like vacuum, but with larger fluctuation, and with the size of fluctuation of the electric field amplitude scaling as square root of n plus 1, where n is a photon number. So it's very far away from what we expect from a classical field with a well-defined amplitude which oscillates sinusoidally as a function of time. And there is indeed a very simple way to generate quantum states which are as close as possible to this classical field. So that can be considered as a definition of a coherent state. Given some energy in the field, what is the way to make a superposition state of photon number so that the average value of the field, electric and magnetic field amplitude, are as close as possible to what they will be classically with the same amount of energy? And the answer is a coherent state, which is indeed defined formally as eigenvector of the destruction photon operator A. So they are characterized by the C number alpha, which is nothing else than the complex amplitude of the classical field that I already introduced. And then this defines the states, and you can develop it over the basis of number states. You get this development where, so alpha is the sum over all photon number states, with here these probability amplitudes, that when you take the modulus Claire, is nothing else than the Poisson distribution, with an average photon number, which is modulus square of alpha. And so the photon number distribution of that is nothing else than this Poisson distribution. So it is here represented for a typical photon number. We'll consider now on average 2 photons of the cavity. So you see that you have significant population up to 6 photons in the cavity. So the C number alpha has a modulus and a phase. So the modulus is related, I already told you, to the average photon number in the cavity. And the phase, if you represent the field by a Fresnel vector in the plane, corresponds to the phase of this vector. So it's really the phase of the complex amplitude of the corresponding classical field. So this looks very much like a classical object. And now I will consider Rabi oscillation of a single atom, not in vacuum, but in this small coherent field, which can be easily injected in the cavity by using a microwave source. So you buy a synthesizer generating 550 gigahertz microwave, and then you put a waveguide close to the cavity, which will radiate some microwave photons, and some of them will enter the cavity. And if the source is classical, the field radiated in the cavity is a quasi-classical field. This can be shown formally rigorously. So now let's just consider the Rabi oscillation, not in vacuum, but in a field containing n photon. Indeed, there is nothing changed except the vacuum Rabi frequency, where you have to introduce the matrix element of A and A dagger in the n and n+1 field states, which amount to add just to the coupling a factor square root of n+1. The magnitude of electric field, which is proportional to the square root of the energy, is the square root of photon number +1, because there is electric field fluctuation in vacuum. So this is very similar to what happened in a vacuum. And now, I'm sorry, 0 and 1 should be n and n+1. This formula. And then the Rabi oscillation, if you are not in a pure state, pure photon number state n, but in a coherent state, it's just the average of all this Rabi oscillation with different frequency with a weight P of n, which is the probability of having n photon in the cavity, so the Poisson law. So again, a very simple equation for the evolution. And then here is the kind of signal we monitored in the 1996 experiment, so the first experiment where we observed the strong coupling. Here is represented again the vacuum Rabi oscillation, and then you see how the signal evolves when you have a larger and larger field in the cavity. And what is nice is that this kind of complicated signal at really just a beat note between a few frequencies. The few frequencies which are related to omega naught square root of n. And this can be determined experimentally by performing the Fourier transform of this various signal. So the second column is the result of Fourier transform. So you see that in vacuum, basically the evolution is dominated by a single frequency, which means that we have a good realization of the vacuum in the cavity, and that we were efficiently removing the black body radiation, which would correspond to like 100 photons in the cavity if it was at room temperature. Indeed, you have a little bit of peak here. You can consider that this is noise, but indeed, quantitatively, it's not noise. It corresponds to an average black body photon number of 0.06, which is the number of photons you expect at the temperature of the cavity that we measure. So the field is well thermalized. And then when you increase the number of photons, you see that this small peak becomes larger and larger. And here with on average 1.7 photons in the cavity, the 1 photon state dominates the spectrum of frequencies. And then you have several peaks. So you can fit the amplitude of these various peaks, and you can fit a Poisson law over there, which is a very good fit within the error bars of the signal. So that's the way, indeed, we get this photon number by analyzing the spectrum of the Rabi oscillation signal. And indeed, these measurements were the first demonstration of the discrete Rabi frequencies involved in the evolution of the excited atom in the cavity. And indeed, that can be seen as a direct manifestation of field quantization in the cavity. I could do this experiment without quantizing the field, and we see that the evolution frequency are quantized. And that's a direct observation of quantization of the field with very little hypothesis in this system. So then, many years after, in 2019, with a new setup with the slow atoms, we performed again this experiment. And you see that we observed the Rabi oscillation over a much longer time scale, as I told you. And a new phenomena showed up, which is very interesting. We observed first a collapse of the Rabi oscillation, and then a revival after some interaction time with the cavity. And indeed, this collapse and revival was predicted in the early days of Rydberg atom cavity QED, and it's indeed very clearly demonstrated here. And so what is the physics of that? Indeed, here are represented all Rabi oscillations for photon number ranging from 9 to 16, because we were dealing with about 13 photons on average in the cavity in this experiment. So you see that due to square root of n+1 variation of Rabi frequency with respect of photon number, all the oscillation are, of course, in phase initially, but after some time, which is relatively short, all Rabi frequency, all oscillation becomes out of phase with respect to each other, and this corresponds to a collapse of the Rabi oscillation, which does not mean that the evolution is not coherent anymore, but that the system is so entangled that you cannot see the individual Rabi oscillation, and the average is just this collage. The time scale of this can be shown to be the time needed so that this oscillation becomes out of phase with that and can be computed easily. Indeed, it's just the vacuum Rabi period, T0, that we already introduced, the period of vacuum Rabi oscillation. But the important point is that the story is not finished there, because after a finite time, as typically a finite number of frequencies are involved in the evolution, they can come back in phase to each other. That you can see here when you sum all these signs. They are again nearly all in phase here, and you observe a revival of the Rabi oscillation. So this was a very clear demonstration of this effect predicted in the early days of cavity QED. First paper about that was written by Eberle in 1980. And indeed, it's another even more pregnant demonstration of field quantization. If you perform the Fourier transform of this signal, as we did for smaller field just before, you see that you resolved all the Rabi oscillation frequencies for photon number between 8 and 19, and the peaks are very nicely separated. So it's very visual manifestation of field quantization, and this was published in Physical Review later. So there is another interesting feature of this signal, but I will come back to that in the last lecture. It is what happened here halfway between collapse and revival. So you see that halfway between collapse of revival, half of the frequencies of a given phase and the other half of frequency of the opposite phase. And indeed, that's a point at which the field is strongly entangled with the atom, and indeed it's already a production of a Schrödinger cat state. So I will not give the details because I will discuss the Schrödinger cat states in much more detail later, but it is here already. And indeed, we have time, I can just show it rapidly on the slide that I eliminated, but which is there. Okay, so here is a kind of advertisement about the third lecture. Indeed, in phase space, the state of the field produced at half revival have the shape of two blue structures which are reminiscent of the amplitude of a classical state. And the important thing is that you have fringes in between, which shows that you prepare a superposition of two fields with very different amplitude, which is a version of what is called a Schrödinger cat state. So we have it here in this experiment, but I will give much more details about this in the third lecture. So let us, okay, so that was additional slides. So let me conclude this first lecture with the message that the cavity QED system based on interaction between microwave photons and circular Rydberg atom is a very powerful and very clean system for achieving the strong coupling regime between single atom and single photon in cavity QED. The last experiment I showed is one of the best experiments in terms of factor of merit of the system, coupling a single atom with a single harmonic oscillator. And indeed, that's a very important property of this system. So it demonstrates first feature predicted as a signature of the quantum character of the field, which was this paper by Eberle, who predicted the collapse and revival of Rabi oscillation. And it was at that time a very popular way to potentially demonstrate field quantization. So this was done in this experiment. And indeed, in the next lecture, I will leave the field of resonant interaction between the atom and cavity to consider dispersive interaction, which is strong enough to produce kind of macroscopic effect, and which is at the heart of the quantum non-demolition measurement technique for detecting photons that we implemented in this experiment. When the atom-cavity interaction is non-resonant, conservation of energy prevents the energy exchange of that we discussed today. But still, there will be phase shift of superposition states, which can be used in order to perform a quantum non-demolition measurement. So I finished here for today. I thank you for attention. You did not ask many questions, so maybe it means that I was too fast, but I hope that there are questions, and let me know if I am too fast. Yeah. Maybe there is.
So thank you for a lecture. Professor. Concerning the preparation of Rydberg circular states,
Yes.
Could you explain a bit more about the, I believe, the third stage of adiabatic transfer? I think it has something to do with an electric field with radio frequency, but
yes.
I got a bit lost.
Okay. Okay. So this is indeed so initially, basically, all the population is there in the lower level of hydrogen-like structure, characteristic of the Stark effect. And then, indeed, if you were in hydrogen, the structure of this energy level is related to a tensor product of two very large angular momentum levels, a big G equal n over 2. And indeed, you can consider that the levels going from here, 52 circular, to m equals 0. So we start with m equal 2 because we are not dealing with hydrogen, but rubidium, but it's a technical thing. So with hydrogen from m equal 2, all the levels from here are the eigenstates of, are the mg states of a big G operator. And then if you send a radio frequency on this, you just rotate. It induces a Rabi oscillation of this big, it can be considered a big angular magnetic spin, and this will rotate around some electric field. So we rather do it adiabatically because indeed we are not in hydrogen. So there are two levels missing, m equals 0 and m equals 1, that's related to the quantum defect of Rydberg level in rubidium. And then the frequencies are not exactly at the frame frequency, and it's better to cross the resonance adiabatically to transfer all the population from here to here. Other questions? Yes. It was, I think we can just.
Okay, thank you. So